Welcome, everyone. We are going to get started here very shortly. Just a quick housekeeping note. Please make sure to look in the participant list and see how your name appears. Make sure that your first and last name are referenced in the participant list. You can rename yourself. That will be helpful so that we can make sure we can report your continuing education credits for attending today. If you do not know how to change your name under the participant list, please chat directly to AIE Pittsburgh's account, and we will make sure that we get you registered or make sure we report your credits. And with that, I believe I'm going to pass this over to Fred to take it from here.
Okay. Hi, my name's Fred Watts. I'm an architect with IKM Incorporated. I'm going to be the moderator for this small herd of cats to try to shepherd you all through this design excellence part 3. This has 4 sections, and we have 5 presenters. Ian Cook will be addressing design for water. Alex Coe, design for resources. Patricia Cully, design for ecosystems. Craig Stevenson, design for energy. And representing FIPS, Brad Klaus will sum up each of those sections individually. Just so you all are aware, this is an AIA CES provider program. This is the standard AIA preamble to those sorts of programs. You're all familiar with that. The course overview is one that most of you are familiar with as well, because you participated in the other 2 sections. The framework for design excellence. We turned it into 4-part program. But this section has section 3 has 4 parts: water, energy, resources, and ecosystems. So those are the learning objectives. You'll be familiarizing yourself with the COTE framework for design excellence, the conceptual questions that apply to each one of those sections, with the COTE super spreadsheet that most of you are becoming familiar with. And then a case study with FIPS Conservancy's Center for Sustainable Landscapes, the local project that we're all well aware of. So starting off, we are dealing with design for water. You're looking at the landscape around the FIPS Center for Design Excellence. That presentation is from Ian Cook. Ian is a building rating systems project manager and an architect at Evolve. At Evolve EA. He does certification management for. He did the certification management for Pittsburgh International Airport. He's worked at the Bridge Review neighborhood development in Bozeman, Montana, and the Greater Pittsburgh Community Food Bank's expansion and renovation. He's also part of the design team for several projects for the Pittsburgh Water Authority. He's consulted on LEED certification for the Gateway Arch Museum expansion. He was on the design team for the Net Zero Energy Jan Phillips Learning Center in St. Louis. While he was living there, he was there for 10 years or so. He's been an instructor and a guest critic at Washington University in St. Louis School of Architecture, and assisted in their 2017 decathlon submission. He's presented as an ambassador for the International Living Futures Institute. He's one of those fortunate people who spent a year at the Auburn University Rural Studio and worked on that project. He spent a semester in Copenhagen Denmark. He's a double Bachelor's of Architecture Studies and Applied Math degree at Hobart and William Smith Colleges. He has a master's from Washington University in St. Louis. He's been a member of the COTE committee since he's been here in Pittsburgh and a volunteer for Habitat for Humanity. He's a registered architect in New York and lead accredited, Eco Districts accredited, Living Futures accredited professional. He's going to be dealing with design for water and answering these guiding questions as we go along. Ian?
Oh, yeah, sure. Thanks, Fred. Appreciate it. Let's see. So I was going to share my screen here. There we go. Okay. Yeah, so as Fred mentioned, framework for design excellence, covering the design for water section. Good design conserves and improves the quality of water as a precious resource. Focus topics for this section include indoor water efficiency, outdoor water use reduction, process water reuse, capture reuse of gray water and or black water, rainwater, stormwater use and management, and net zero water buildings. Topics for consideration within the section include how does the project use water wisely, addressing efficiency and consumption while matching water quality to appropriate use. How can the project's water systems maintain function during emergencies or disruptions? How does the project handle rainfall and stormwater responsibly? How does the project contribute to a healthy regional watershed? Brad will explain how this was realized in the CSL and the Phipps Conservatory campus and what the water portion of the super spreadsheet looks like. But first, I'll go through a few brief high-level examples within the work of Evolve VA and previous work project experience. These were quite a few of these projects from before I was at Evolve VA, so these going back a little bit, but this is upon its completion in 2003, the David L. Lawrence Convention Center was the world's largest green building at 1.5 million square feet and was the first LEED certified convention center. Evolve VA and its consultant team was hired by the Heinz Endowment and Sports and Exhibition Authority of Pittsburgh and Allegheny County to perform a post-occupancy analysis of the DLCC's green features, including water systems and existing data collection. The Evolve EA team guided the LEED existing buildings pursuit, and the study culminated in the facility becoming the first LEED EB Platinum Convention Center in the world. Some of the water features from this project include aquifer, they're used for landscaping, irrigation, and cooling tower feed, gray water reclamation plant, water usage reduced by 66%. The next slide here, the Frick Environmental Center. So Evolve VA worked along with the design team, including Patricia Cully, who's on the presentation here as well, to help guide the project through the Living Building Challenge, planning, design, and certification process. Many aspects of the center's design combine strategies that holistically address its integration with the landscape. The parking area, for example, features permeable pavement and is covered with trellises that hold solar panels and collect rainwater. The building is responsive to its natural environment through sustainable landscape best practices. It is also designed to manage all storm and wastewater on site. This next project here, the Ross Reserve through Purdue University, Evolve VA guided the development of this project from its conception through the design process. Site location, building, program, and form were carefully considered throughout the process with scenario testing for water calculations. The client's commitment to living building principles gave an imperative to achieve net zero water use in the building's design. Just as the biological organism seeks homeostasis using feedback loops to adjust to changing conditions of its environment, the architecture frames and captures site forces such as stormwater, wind, and plant communities. This next one, a current project. So Evolve VA is currently working on a number of projects along with the Pittsburgh Water and Sewer Authority. Investing in the infrastructure will reduce water loss. Many of the pipes in the system are over a century old, and incremental replacements with modern fittings will reduce water loss over time. PWSA is making significant investments now on major components of the distribution network. Water is a single resource that connects us all, must be managed collaboratively. So sort of an overview and an interesting little throughout the Pittsburgh region. The next project, next slide here, from previous work, the Jan Phillips Learning Center is an offsite extension of the College School's urban campus in St. Louis, Missouri, and expands on their mission to engage and captivate students through nature-based experiential learning. Rainwater is captured and reused, composting toilets reduce water consumption, and make use of natural resources that would otherwise be wasted. An aqueduct feature helps create not only a place for learning, but also spaces that can be learned from. So there's the aqueduct feature there, the sort of concrete retaining wall. Let me see. So the scope included providing a feasibility analysis and creation of a master plan of the overall site. Great effort was made to protect LeBark Creek, which is located on the property and is one of the most pristine tributaries to the Merrimack River, which then flows into the Mississippi. That was the section on water, and those were the projects that I was covering here, so I can stop sharing. And then I don't know if it was Brad was going to take over at this point. Or on to Craig. We're going with Brad next.
Yeah, thank you, Ian. Let me pull up the screen share. Thank you, Ian. Yes, so throughout the previous two workshops and then during the course of this third workshop today, what we've been doing is sharing, taking our Phipps Center for Sustainable Landscape project, which it's an on-site building at our Phipps campus that houses our administrative staff as well as some of the environmental education programming. It was constructed in 2012. It is a certified living building, so you'll see some of the features that I'm going to highlight here in the resulting three topic presentations. Going to sort of emphasize those principles that are contained within the Living Building Challenge certification process, especially related to water, energy, resources, and ecosystems today. So what is the sort of highlight of what Ian was showing before from the design framework for design excellence, principles that I'll try to reflect in not just how I share how we completed the COTE super spreadsheet tool to respond to the specific questions in that tool, hopefully share some examples of our experience completing that tool with everyone that will be useful, and then how the actual project itself reflected as it relates to not just the framework for design excellence sort of guidelines and parameters, but also the specific questions asked, referenced it in the COTE super spreadsheet tool itself. So the first question contained within the COTE spreadsheet tool is sort of some of the basics. It's looking at what is the overall estimated indoor water use. There's actually a tool embedded in the spreadsheet that will, if you don't already have your own estimates to input into the tool, this actually has a basic calculator for you, which you'll see here highlighted in the center are basic fixture flow rates. So in terms of getting something that's easily ascertainable or referenced from the specifications for your project, you've got toilet, urinal, shower, lavatory, kitchen faucet fixture, specific gallons per minute rates that you can easily pull from those spec sheets. And it will give you a calculated estimate of the total indoor water use. Obviously, when I completed this, what I tried to do was pull the specific, just for demonstration purposes. These were the fixture rates that we had. The only one that we didn't have information for was the shower, because there are no showers within the CSL facility itself. Second question is, and I think this explains why some of the fields you'll see in this corresponding irrigation estimator did not complete or did not produce numbers, was because I answered specifically for the CSL project the question of, is potable water used for irrigation? The simple answer for our project is no. It's all rainwater harvested that we use for irrigation on the project site. So I think that explains why some of the fields didn't populate. You'll see some blanks under annual irrigation water use calculation. I believe if you answer the question no, I think the spreadsheet will not populate that for you. So in this case, there were some parameters that we pulled from the project site itself for CSL. The irrigated area estimate of 65,000, roughly 65,000 square feet. The climate zone for estimating evapotranspiration, plant quality factor, which sort of was a range of water stress to non-water stress to what I qualified as baseline, our estimates are based on a typical precipitation event or year. Type of plantings, our planting plan for the project involved all native plants, so that was an easy one to specify. And then irrigation efficiency, we do have a small amount of drip irrigation, but we also still rely, unfortunately, on sprinklers in a lot of cases to irrigate when we don't irrigate a lot, but when we do use sprinkler systems for that purpose. Cooling tower section, again, recognizing that this is probably applicable to a lot of project sites with a larger cooling capacity, you would need to fill some of these fields in. For us, it was a simple answer because we don't have cooling towers or chiller systems that are involved in the project or associated with the HVAC systems at CSL. So our cooling tower water usage was 0. And non-applicable was what we responded to sort of the other questions related to cooling tower water efficiency. But certainly having worked with cooling towers before, I understand this could be a significant source of water use at a site that does use cooling towers for its HVAC systems. Second section of the water spreadsheet actually looks for a combination of predicted or modeled water usage compared to what the actual measured performance period of water use was. For our project, we actually had a formal performance period through the living building certification process, so I was able to easily extract that 2014 full year performance data. So the numbers you see represented here will actually show you how the site performed. The model numbers are largely estimated calculations based on precipitation for the rainwater extrapolated out over the year. So rough estimate of a evenly divided precipitation across the 12 months of the year. And then reclaimed gray and black water was estimated based on the potable water is that's discharged to the sewer is all treated on site and then reclaimed to be reused for toilet flush. So all that water, this is basically an estimate of what our fixture flows that would be put into the system would be, and then extrapolated out over the year. All said and done, the estimated total annual gallons was coming out somewhere on the measured side around 87,000, just under 90,000 gallons per year. And you can see the breakdown. It partitions it by potable rainfall or rainwater that was recaptured and reused, as well as gray and black water reused at the campus. Overall summary, again, I think it didn't produce some of the predicted numbers you'll see in that first section because the tool was missing irrigation, but on the measured piece, it's a little unusual because it's a net, because the site is net positive water, the numbers will come out negative. So what this is showing you is that roughly we harvest 57,000 gallons more water than we actually use potable water at the site from a municipal source. And then that sort of breaks it down into a occupant estimate of how much per occupant and then how much per square foot of the site itself. Both of them being negative because we're in a surplus situation at the site. Sort of give you an idea of where they stand against the benchmark site, similar sort of size would be roughly 350,000 gallons per year of usage, and ours was coming in around 7,900 gallons per occupant per year, so a substantial decrease. And then when you look at the overall improvement metric, it's saying it's in excess of 100% since we're actually net positive water. It's actually saying we're harvesting more water than we're actually extracting from the municipal source. Stormwater management, sort of the other key component of the tool and the water measure, focuses largely around what the storm events would be. In this case, they're looking for a 24-hour, 2-year event. This was all something we were able to pull from our existing data in our stormwater calculations. So I was able to go back to the reference design information for the stormwater systems at the site, pull out this 2.35-inch 24-hour, 2-year event for our region in Pittsburgh. Then there's a calculated storage capacity for all of our combination of our retention bases. We actually have some infiltration galleries with fixed storage that are not lined and infiltrate into the subsurface. All told, we've got about 13,000 cubic feet of capacity for rainwater storage, which is pretty enormous. So you'll see in the overall calculations and measures of efficiency of the site, it's essentially managing, at least from a 24-hour, 2-year storm event. 100% of the stormwater on our site would be handled on the site, won't ever leave the site. Then the last question it's calling for was related to the treatment of stormwater that was conditioned on the site. So I think it was a scale of 1 to 5, and I believe my response was 4, which was just below the maximum or highest score you can get, which was the runoff is mostly treated through natural filtration, combination of rain gardens, bioswales, and retention for infiltration purposes. So that in and of itself was I think the other one, the last category was you would have to actively treat your stormwater, which we don't necessarily do. We have a few catch basin sedimentation filters, but I wouldn't necessarily quantify that. It wasn't really fair to give us credit for active treatment of this stormwater. It's all natural forms of treatment that we're using for our rainwater on site. Just some of the features specifically that we highlighted up against the questions that we're pulling against this topic for standards for a framework for design excellence. Number one, starting with the basics, we have high efficiency plumbing fixtures and waterless urinals, so we're reducing the actual demand for water. Our planting plan in the landscape, it's all native planting and ultimately shouldn't necessarily require, unless there's some sort of water stress, a lot of supplemental irrigation. We're harvesting rainwater and storing it. So when we do need to irrigate at the property, it's not coming from potable water sources. We're actually harvesting that stored rainwater to do any irrigation at the site. There are a few minor service uses, which we use for miscellaneous sort of non-potable purposes for cleaning things and equipment related to facilities as well, that goes into that usage. All the black water and gray water is treated at the site, on site, and then reused for the purposes of toilet flushing. Stormwater filtration and treatment is occurring for all the stormwater that's impacting or coming onto the site through a combination of our on-site lagoon and wetlands, the rain gardens themselves, as well as some catch basin filtration systems. So we're pre-filtering it, and now everything that's going into those catch basins and from all the pervious surfaces is actually being routed through those rain gardens or underground infiltration galleries. Stormwater infiltration and recharge, again, we've got a series of online tanks that I mentioned just before, where we have infiltration occurring subsurface, as well as a couple of sections of permeable pavement that were installed in some of the parking stalls that are associated with the project. Sort of that all results in sort of pretty impressive, especially for the Pittsburgh region, where we have such a problem with combined sewer overflow volume. We would have modeled no offsite stormwater discharge up to a 5-year storm event, which is a 2.87-inch storm event within a 24-hour period. And if you go even to a 100-year storm, we're talking about nearly 80% reduced offsite impacts in terms of stormwater flow leaving the site. So all those are quite impressive. It's hard to find anything that matches up to that. In terms of the last question, and in terms of how we're benefiting the overall watershed, there's a number of principles that the site systems are supporting there. We're doing pretty much everything, or under normal circumstances, everything is being recharged to groundwater at the site. So we're ultimately recharging the aquifer within the watershed, replenishing that. We're reducing the actual water demand from PWSA in a number of ways, because we're actually taking some of this harvested rainwater from this site and using it at other parts of the campus to offset our overall campus water usage, not just the project site itself. We're reducing that runoff and ultimately some of the flooding problems, which are all too familiar with in the Pittsburgh area. So we're reducing the impacts of that sort of surge of water during these heavy rain events in the region. And ultimately, with the treatment on site, any water that does leave and anything that's going and recharging to the groundwater is always being pre-treated naturally through natural processes before it's actually recharging back to our watershed. This is just there we go. It's an overall diagram that we've created to sort of illustrate what the process flow is for our rainwater system. So you'll see there's a capture system. We're actually capturing some of the rainwater that's not from the project site, from our tropical rainforest roof, harvesting that and storing it so that we can use it for a backup for toilet flush system, as well as for all of our irrigation and other needs at the site itself. There are a number of other areas where the actual groundwater flow is feeding the on-site lagoons or other sources of storage at the site. So this big blue section that you just see illustrated here is actually a combination of a lined underground storage tank and an unlined storage underground storage tank. So the surplus water from runoff that actually would either exceed the volumes of the rain gardens could be overflown into that unlined tank for additional storage capacity. And then that much larger underground storage tank is a reservoir of stored rainwater from various different rooftops at the site, which we can harvest not just for the purposes of use in the CSL, but also for use at other parts of the campus, larger campus. So that's sort of the last representation is that there's a second upper storage tank that we pump water to, where we can actually pump that to other parts of the campus, mostly in our production greenhouse. And this is actually a similar replication or demonstration of what the system for our on-site wastewater treatment looks like. So all the gray and black water from the CSL goes into first stage of treatment, which is basically a traditional settling tank where the solids are removed. And then from there, it passes into a constructed wetland for biological treatment. After it passes through that constructed wetland, it then goes through a series of recessed in the ground sand filters for a more formal mechanical form of treatment. And then ultimately it's recollected in a cistern, which is then pumped to a temporary storage tank, which we have adjacent to the building, where it can be harvested and recirculated for use in flushing the toilets at the site. This additional system that you're going to see represented here was originally planned to take care of the excess volume that we accumulate over time from the reuse water system. And the original intention was that this would be used for evaporative distillation on one of our rooftops of our production greenhouse. Unfortunately, this is an example of a technology that didn't pan out the way we're always innovating. And in this case, the innovation didn't pan out the way we expected it to. So that water now is currently still being collected, and we're trying to find an alternative use for it, since this technology for distillation didn't quite do what we expected it to do. So that piece of it is something that we're probably going to either do additional treatment to that black water so that we can apply it for irrigation somewhere else at the site. This is just another picture of our beautiful lagoon outside the CSO, which is part of our natural treatment systems for stormwater. You can also see nicely represented here some of the various different stages of the native planting that was introduced as part of the site development. This actually is a good aerial view that gives you the sort of view of the lagoon and how it's ultimately interconnected and associated on the property with our constructed wetland. You can see highlighted there, sort of gets lost in the green, but underneath that there is actually a constructed wetland that is performing water treatment, sort of disguised into the landscape. This is gives you a better idea of what it looked like during construction. So yes, it is there. There are it's a two-stage or two-cell section constructed wetland for biological treatment of our wastewater from CSL. And you can actually see what the lagoon looks like before it was actually completed. So there's a big liner that's set underneath the lagoon itself that was laid out during the construction phase of the project. These are the two primary rain gardens, which all the pervious surfaces, paved surfaces, ultimately redirect the water into one of, these are two, but we also have a third on the corner of the CSL building, rain gardens, which are designed to allow infiltration and natural treatment for stormwater that's collected on our pervious surfaces, or impervious surfaces, I'm sorry. This gives you some idea of how enormous the underground storage capacity is. So what you see here is the installation of that same picture I just showed you of the parking area and the two rain gardens. That is actually built and constructed over these two tanks. So the tank you see further to your left or closer to the building, that's the line storage tank, which we actually collect and harvest rainwater from for reuse at the site. The second to the foreground, Second to the foreground is an unlined underground storage tank, which is designed primarily just to take excess flow from some of the rain gardens and any additional flow that can infiltrate, sort of function as an infiltration gallery, as opposed to a storage tank, which we can actually recover water from. This just gives you another sort of stage of the construction. You can see what it began to look like before it was actually capped, the surface of it, with the rain garden and with the pervious surface of the asphalt. And this is the upper cistern storage tank, which is used to collect the stormwater runoff from our tropical forest roof, which we also harvest and use for backup and irrigation for the CSO and the green roof on the CSO. This gives you an idea what the sand filters look like. You see them today. They're basically hidden underneath the lawn in the front of the building, but buried underneath there is the system you see here, sort of sand on top of a drip system that disperses the water and lets it percolate through the sand, and it's then collected at the base of that sand filter and collected in an underground cistern where it's pumped for reuse in the building. And that covers everything for the water portion of our CSL project.
So next section is energy. And our presenter is Craig Stevenson. Craig is the founder of a company called the ROS Group, technology consulting company here in Pittsburgh. He's been an activist and a leader in sustainability and evidence-based performance for the built environment since he's been in town. He's got 25 years of construction experience in estimating and all sorts of building performance standards. He's a co-author of a newly released book called The Power of Existing Buildings: Save Money and Improve Health and Reduce Environmental Impact. He's also a holder of a couple of patents in the field of data science for the built environment. He's going to deal with design for energy and these guiding questions that relate to design for energy. Craig?
Thanks, Fred.
I'm sorry, let me mention too, that we're going to deal with the questions and answers at the end. So if you put your questions in the chat, we will compile them and try to answer all the questions at the end of the program. So Craig, go ahead.
Thanks, Fred. It's great to be here and talk energy with you guys. It's nice to see a lot of familiar names and faces too. So I've been asked to summarize energy using passive first strategies in 15 minutes or less. So we're going to have a lot of fun. So as we get into it, we like to start a discussion around energy by looking at the history of sustainability. It's always healthy, I think. It's always beneficial to understand where we've been, to understand where we're going. And if you look at the timeline, when we started the conversation back in the 60s and 70s, it started with conservation and activism. Then it went to prescriptive standards and then performance-based standards. And now what we're seeing in the market is performance accountability. When you look at the legislation that's being passed in states like California, even the city of Pittsburgh with its zero energy legislation they passed last year for all city-owned buildings, we're quickly moving into an accountability phase of construction projects where it's really focusing on outcome-based design decisions. When you deal with outcome-based design decisions, you really have to start to understand how you get there, right? What does the end game look like? This idea that LEED has taught us and other sustainable certification programs have taught us is that you start at code-based construction and you work your way down, right? I want to be this much better percentages wise based on ASHRAE or based on code-based standards. And we always work our way down. When we do that, we find that we might get 10 or 15, maybe 20% better than code-based standards. The other way to look at it, and what we're seeing a macro trend in the market right now, is starting with a bottom-up approach. The question becomes, from a building science perspective, what is the most efficient building we can build? Passive house really kind of leads that discussion. And then when you consider that with the natural order of sustainability, what is the natural order of sustainability? It's a passive first strategy, right? Active second, renewables last. We wanted to make all of our decisions around the envelope: massing and orientation, envelope optimization, climate specific thermal values, to maximize our passive strategies. That reduces our loads. Once we reduce the loads on the building to a building science maximum, then we want to start to ask ourselves, okay, what's next? Well, let's look at our active systems. What happens when you get to those low loads is you start seeing decoupling happening. We're going to deal with our ventilation systems with energy recovery. We're going to deal with our heating and cooling systems with systems that we wouldn't have otherwise used, like VRF, for example. You know, in a code-based structure, that might be a very expensive solution that we simply can't afford. But when a passive house project, or a project with very low loads, that becomes a very real strategy. And renewables last. And why renewables last? Well, if I do item 1 really well and I do item 2 really well, my photovoltaic array is only going to be this big instead of this big. It's more affordable, and the maintenance and life cycle costs on are going to be much more reasonable. So what we're seeing, and when you take an envelope first approach, is you want to understand what the end game looks like. You want to start there. And why aren't we building passive houses across the country? Well, a lot of people will argue because of costs. We don't agree with that outcome. We've seen projects being put up for par, and I'll show you a few of them today. But if that's the reason, then start at a 14 EUI and work your way up. There, you're going to find that, you know, you're going to tunnel through that cost barrier where you look at the systems and you get to that click point where you get to this next system. That's where you're going to start to see the major efficiencies happening. And when you do it this way, you end up with a 20 or 30 UI and you still win, as opposed to working your way down. So the Passive House Accelerator is a really great resource if you're looking for resources. Google it, look it up, but they're a great resource for a lot of these building science methodologies. And they have this image that they use, and I really like it a lot, so I kind of borrow it wherever I can. And they talk about, you know, zero carbon. How do you get there? If you ask 10 people, you're probably going to get 10 answers. But when you start looking at it from a building science perspective, there's really one way there that's going to be the most cost-effective way before, you know, it's going to not make you spend a premium in cost of construction, right? So energy efficiency, maximize your energy efficiencies as much as you can per building science. Then minimize your carbon, your embodied carbon, that's materials, right? And then electrify everything. I can't offset gas, right? So why am I going to have gas into a building when I can't offset it? I want to electrify it. A lot of people are going to argue, well, gas is so cheap, why don't I just do that instead of electric? It is, but when you're at a 14 EUI, that delta is much more manageable. When you're at a very high EUI, then that's right, gas is much cheaper to do. And that's, if you don't look at it from the bottom up, you're going to make decisions that aren't really necessarily beneficial for the long-term viability of that building. And renewables last, again, you want to offset whatever low energy consumptions you have on that building with renewables. That's how you get to zero energy carbon. That's referred to as the natural order of decarbonization, which is kind of interesting. And what you'll notice here is these 3 strategies for energy efficiency, electrify, and renewable energy, they are enabled by the natural order of sustainability. So where does the money go when we start looking at envelope first strategies? We know we're going to invest a little bit more money in the envelope, right? The insulation thermal barrier is going to be a little thicker. We would argue that the air barrier goes in most buildings. Unfortunately, it doesn't get tested in most buildings, but it goes in most buildings. So that should be relatively par. And the windows and doors become a little more expensive. That's true in certain climate zones, but we get the money from the mechanical system. So rather than putting a 300-ton air conditioning system on the roof, that becomes a 50-ton system. We take the money from that, we put it in the windows, and that's how we basically get the cost parity. And we'll show you the differences between small buildings and big buildings and why this strategy works way better for big buildings. I'm going to have a few slides on how we're going to show that. And another thing here is insulation never breaks, right? So if we take a passive first strategy, that's going to be in place for 50 years if it's done right. And if it's QA/QC'd right, insulation simply just doesn't break. It just lasts. And it's really a simple idea. So the image you see on the right is the image of our executive director at the North American Passive House Network. That's his house, that's his kids. They're sitting on a windowsill in the middle of winter, and they're very comfortable. And if you've never been into a passive house, I would urge you to go into one. find one. Carrick Library is a public passive house project. Walk in there in the middle of the winter time. You'll see the buses going up and down the street. You don't hear them at all. You don't feel them because basically you're in a soundproof barrier. There's so much insulation in there. And if you put your hand on the window and then you put your hand on the jamb, you're not going to feel delta in temperature. That's really what a passive house is all about. It's a simple, simple idea of keeping your energy and not just sending it out into the environment. So what does that mean? If you think about it from a passive house perspective, if you really want to use building science to get there, there are 5 key principles. Climate specific insulation levels. Now we might say, okay, well, we're already at climate specific insulation levels. What Passive House has done is they've identified the law of diminishing returns. When does the envelope stop paying? Does it stop paying at an R38? Does it stop paying at an R50? You know, we've been on projects, we've been invited to projects where they're doing a re-roof and they specified an R50 and we asked them why. And they said, well, we want to save energy. Did you model it? Did you know that that's your efficient level? And after we basically got into the project and we identified their low energy solution, they ended up going to an R32. They didn't need an R50. So they were kind of overshooting it because they just didn't understand the processes. So it's climate specific insulation levels. It's going to be specific for the orientation and massing and the locations of that building. And it has to be continuous. Thermal bridge free connection, right? There's so many projects we've been brought into where there's just massive thermal bridgings, and thermal bridging is just an energy highway. It's how energy leaves a building very quickly. You know, we've seen brand new buildings get built with a front entry that the steel literally just punches right through the envelope and no one thinks anything of it. And it's just, that's not the right way to start approaching this, because it becomes a durability issue very quickly, but it also becomes an energy issue. And there are better ways to do this. And there's just a running joke in the passive house community. Once you see a passive house detail, you don't unsee it. So even if you're not doing a passive house project, these details are just the right way to design buildings from a durability, a thermal comfort perspective. High performance windows. Again, they're going to be a little bit more expensive, but they should be offset by the cost of the systems. Air tightness. Again, people are going to say, well, we've been doing air tightness for a while. Passive house's air tightness is a 0.6 ACH at 50 pascals. To put that into perspective, average code buildings getting built are between 4.0 and 6.0. This is a 0.6. It's tight. And you don't get to a passive house air tightness by accident. This takes expert detailing, people with experience to understand what they're doing. And it takes a construction team that's been trained before they start putting in the air barrier. And highly efficient heat recovery ventilation. Again, you'll notice that this is just dealing with ventilation. It's decoupled. So you're going to see a lot of DOAS and ERV type solutions with energy recovery. We want to capture our energy. We don't want to pressurize our building to deal with infiltration and exfiltration and then push all of our heating and cooling outside and have to repurchase it all again. That is not an efficient way to manage a building. Heat recovery is definitely the best way to do it in an airtight building. So there's a mantra in passive house: maximize your gains and minimize your losses. It's all about balancing. When you get into a project for a passive house, you're balancing everything. It's, you know, someone told me at one time, it's like having 6 dials and you're moving dials to figure out, I want a little more wall insulation, a little less U value in my windows, and you start dialing then. It's all about balancing the energy balance for the optimum performance of a building. So you're optimizing the thermal enclosure, you're optimizing your heating gains, and you're optimizing ventilation, and you're doing this all in the context of a whole building. And this can only be done with an energy model. You can't put a thumb in the air and kind of guess your way to it. You really have to use energy modeling whole building energy modeling to answer these questions. And again, this gets at active systems with smaller loads, decoupling, and ventilation with balanced energy recovery. So these next 3 slides are probably the most important slides that I kind of grabbed based on the time we have here today. And I can't tell you how often I've been on projects where the teams have simply just disrespected building science, and you're seeing buildings that, you know, have crazy massings. But having said that, I understand architecturally we want to build beautiful buildings. But if you understand your surface of area of walls to volume of air ratios, and you understand what good and bad looks like, you can start to manage that. We are on a project, I'm going to show you a case study in a little while, where they had juttings on the building that was adding our surface to air, and it was making it challenging for us to hit our energy projections. And we basically got them to a position where they were able to basically bring the thermal barrier back to a nice thermal barrier, which was squared off and easily manageable. And they made the juttings on the rain screens, and they got what they wanted from the building. It's a beautiful building, but they did it without basically dancing the thermal barrier. And that, to me, is a creative way to solve the problem, right? We don't want to build igloos. That's ugly, and no one wants to do that. We want to build great buildings, but you still have to respect building science. And what you can see here is, this is why I mentioned earlier that large buildings are easier than smaller buildings. When you're in a smaller building, that envelope becomes really critical and super important because there's not enough of it. So when you're dealing with that, you might have an envelope here that's really thick, and it's larger than it would be for a larger building because your area, surface of area to volume of air ratio is so out of whack. So, and I'm going to show you another slide here on the dimensionings and what that looks like. But just rest assured, this line right here, you're seeing this dotted line, this is really your inflection point. When you get to this point where you're dealing with 2 stories of that approximate size, passive houses become much, much more affordable to do. And as a matter of fact, we would argue that they're par at that level. You're no longer paying a premium. You can also do it by looking at the surface area of the floor ratio. Again, not as accurate, but if you're talking about early conceptual massing and you're just looking at a building to see what your massing might be best suited for, then basically take an SAR value at it, and you can look at this. And again, here's your targets for really good buildings, 0.8, and really, challenging buildings, 4.0. Again, you can do this. I would argue that the surface of wall to volume of air ratio is a much better way to take that early analysis, but you can certainly do a really quick analysis with just surface of area. This is the slide I was telling you about, and you'll notice here, this is the massing heat loss form factor. And you'll notice here on these small buildings up here on top, your insulation value is getting to 17 inches and 12 inches. And that's what we're seeing on small buildings. Again, the envelope becomes critical. It's not enough of it. It's so small compared to your area of volume ratios. But then when you get into the larger building, now all of a sudden you're seeing 2.7 inches. That's why it's much easier to do passive house at a 14 EUI for larger buildings. You just have to manage your details, because then all of a sudden the thermal bridging and your transition details for your thermal barrier and your air barrier become much, much more critical. And it's less critical that you have 12 inches of external continuous insulation. So this is a really important slide to keep in mind when you guys are starting to think about orientation, glazing, shading, how you optimize your solar gains and losses. This is where slides like this become very helpful in early conception when you start considering your passive house envelope for continuous insulation, thermal bridgings, and air barriers. If you do everything right, it becomes a win-win-win strategy. There is a reason we lead on all the projects that were brought in to talk about with passive first strategies, because when you solve for passive first strategies, it leads to everything else. When I have a tight building, I control infiltration and exfiltration. I'm keeping the outside out and the inside in. When I want to ventilate, I'm bringing it through my ductwork in my filters. Now all of a sudden that fixes indoor air quality very quickly. So you can see that the envelope is the pathway to indoor air quality. And when you say that to most people in the industry, they just think like, there's no way that can't be true. And it's absolutely true. The envelope is the key to IAQ and IEQ. And that's what you're seeing right here. It's the key to comfort. When Passive House was created in Germany about 30 years ago, 35 years ago by Wolfgang Feist, he did it for thermal comfort. That's the reason why they started Passive House in Germany. Thermal comfort. It wasn't an energy issue, it was thermal comfort issue. And then they said, well, wait a second, if we do it this way, we also get after energy and we also get after indoor air quality. So then you could start to see why all this kicks in. Resiliency. Why resiliency? Because insulation doesn't break, like I mentioned before, it just lasts forever. There's a study in Katrina, when Katrina hurricane hit New Orleans and all those buildings lost their power. If they were in a passive house, the lag time for a passive house to go 2 degrees is like 2 weeks. If you keep your windows and doors shut and just come and go as you normally would, that building is going to stay at that temperature for a longer period of time, certainly longer than what they had down there. U.S. Army Corps engineers actually started implementing passive house because of Hurricane Katrina. And again, this is how you do a renewable transition, because now all of a sudden we have affordable photovoltaic arrays. So I told you, I promised you guys I'd give you a few case studies. This project here is the East Liberty Presbyterian Church. I'm sure most of you guys are familiar with it. When we were brought into this to this area, we were doing a mechanical retrofit for the church. And we started to take a passive first strategy. And you might wonder, like, how the heck do you do that? It's all limestone. And it is. But we basically created airlocks around the entrances. We were able to basically contain air that way. And all of the existing windows were basically treated. So we sanded down all of the pitting for the aluminum, and we put new gasketing in. We did a blower door test on this. It was the biggest blower door in Pittsburgh at the time. And we were able to basically reduce their energy performance by 30%. We used passive first strategies. This building became a Reset Air certified building. Reset Air is an indoor air quality standard. If you don't know about it, you probably should Google it and check it out. There's a lot of Reset Air work going on pretty much everywhere. Every project that we're doing is a Reset Air project at this point. And this building is also a smart building. So it is tracking and trending digitally all of its mechanical systems, all of its utility consumption, and reset indoor air quality for Reset Air. And these are just some images about the dashboards, and I'm more than happy to show the dashboard. It's a public dashboard for this. If you need it, just shoot me a quick email. This project is in Wheeling. This is the Highland Sports Complex. It was constructed last year. And you can see it's a pre-engineered metal building, but they have 3 soccer fields under roof. They have 8 basketball courts, and then there's an interstitial space that's traditional. We were able to create an air tightness in the interstitial space. Pre-engineered metal buildings, can't get an air barrier too much in those, but we were able to use it elsewhere. And we were also able to use, because there's pre-engineered metal building, a DOAS with heat recovery strategy in the pre-engineered metal building structures. And again, passive house strategies, but not passive house. We lowered our energy consumption. We're still monitoring it. This is a smart building. And this is the first topology for Reset Air. This is the first sports complex in the world that's Reset Air. This is also, we submitted our documentation for well building certification a couple weeks ago, and we have every anticipation we'll receive that as well. So this will become pretty much the healthiest sports complex in at least the United States that we know of right now. And again, this is a smart building. You'll see that it's tracking using simulation from all the modeling work that was done, and it's superimposed on the dashboard. So now the question becomes, what was the building designed to do? And are we getting from that building what we wanted to? So this building is pretty interesting in the way in which it tracks energy. The last case study I have here is a project that's in Uptown. This is the project that I mentioned where we went through some really interesting massing studies with the architectural firm on this project. And all the juttings that you're seeing here, and even the windows, all this is basically done with rain screening and trim. The thermal barrier is actually behind it, and it's managed very, very well. This is going to be done with offsite construction, and this will be a PHI certified passive house project. We've already hit all of our numbers on this project. And it is going to also be a Reset Air project. This will be the first topology for multifamily. There's 171 units of multifamily here. This will be the first topology for Reset Air on a multifamily, and this will also be a smart building. With that, I will pass it back to Fred.
I think Brad will fill in here with the case study from CSL.
Thank you, Craig. And Fred, I think you'll definitely see when I get into the slide. Okay, I think you'll see that a lot of the principles that Craig was just describing, especially sort of with the early slides he was sharing about where we starting. I think our project will definitely, see in what I'm sharing, it emphasized how we're starting from, start from sort of passive with everything, and then sort of passive, active, and then minimize what we would need in terms of our overall offset. And certainly we meet electrification, so that all those principles you'll see will line up with the CSL. Obviously, this is from 2012, so things have even sort of, moved along even further in terms of passive house design since then, but a lot of the same principles you're going to see emphasized here, and reflected by the performance metrics that you'll see in the tool itself. So this is the first inputs into the COTE super spreadsheet pool are similar to water, just an overall evaluation of what the predicted, in this case, our energy model was anticipating for the usage in the building versus what our actual measured performance period was, which is what you see highlighted here in the chart. Just to sort of, the nice part of our CSL in this regard is it's simple because it's electrified. So we only have two parameters, grid electricity in the model and on-site generation. Similarly for measured we have grid electricity as well as renewable generation. So it certainly made the process simpler, and obviously for some of the other projects that you'd be completing this tool for, you may have combustion sources like natural gas, chilled water systems, or possibly even in Pittsburgh district steam for meeting some of your HVAC loads. For us, it was a sort of simple exercise to go through and pull. The model had monthly output data that we were able to extract for what our anticipated usage was. Our solar provider had estimated production outputs from the system size for the site to offset our electric usage. And then during the performance period, similar to many high performance buildings, we've got an extensive metering capability for the CSL. So not only do we measure the overall usage for the building, we sub-meter everything down to, in some cases, individual loads. So in this case, it was easy for us to pull the total usage from the performance period. And we also monitor from each of our individual inverters through the SMA Sunny Portal monitoring system, all the output from our renewable generation systems. And in the case of the CSL, there's two forms of renewables that are offsetting the energy use. One is a small wind turbine, axial wind turbine, which I'll show a few photos of in upcoming slides. And the other is a fairly robust photovoltaic array of about between 125 and 130 kW capacity. So I think the most interesting thing that's reflected out of the first step of this was the comparison of our site's performance to the benchmark. And this sort of goes back to the other, what is the benchmark site? If you went along that scale that Craig was referring to before, you're looking at this building being, a small percentage. And in this case, if you take the benchmark site, we were ultimately only 20%, or like roughly 1/5 of what the benchmark site's usage was. So through all the individual measures that I'm going to describe in the upcoming slides, we were able to get sort of the site's overall usage down to a point where it was reasonable from a cost perspective to actually offset the production with on-site renewables, in this case, photovoltaic and wind. I did include our specific cost per energy just for the cases of in the case of the exercise. Natural gas, obviously, we don't use, but the grid electricity purchase price we're at roughly 7 cents per kilowatt hour that we're purchasing from Duquesne Light at this point. But you can see there's this considerable reduction from a benchmark site's production, where 442,000 roughly kBTU, whereas the benchmark site is over 2 million. So reflecting on the specific questions of what strategies we employed specifically for the CSL, it goes back to what we were referring to before in terms of starting with what were the passive components of this that we put in place just simply to avoid having to actually do anything active and in terms of energy input for conditioning the site. So one big one was early on in the process was orientation of the building so that we could maximize daylighting and passive solar heating. So you'll see in one of the upcoming slides, I'll share where the building's oriented so that it's picking up, certain south-facing elements of the building to maximize those parameters. Natural ventilation. So we have the capability when the outdoor conditions warrant it to open operable window vents and roof vents, as well as a large number of the door systems. We have a lot of glass walls and folding door systems on the main vestibule of the building that can be opened up. So certainly this time of year and in the fall, there are a lot of days where we're able to actually take advantage of natural ventilation to condition the space and bring in some outside air. We also have a green roofing system on the third story. There's not only the sort of traditional green roof benefits of stormwater runoff reduction, but also there's some insulating properties that it's offering us on the third story, on the second story or the third story of that building to minimize in terms of the envelope itself, in terms of the heat load of the building. You'll also see there are some thermal mass materials, particularly in our lobby, and we actually have not put this in place yet, but we added the capacity in that space to install its pipe with radiant heating capability. So we actually are exploring the possibility of putting that in place now, where we'll have a greater degree of control over the atrium space, particularly on the really cold days in the winter, just for a sort of occupant comfort standard. There are some days where when it gets really bitterly cold that we would like to have the ability to supplement some of the heating in that space to make it more comfortable for guests. Phase change materials, which is sort of a unique one that was explored in this project. I'll share with you the specific technology we used in one of the upcoming slides. And select walls and ceilings, we were able to work with the local university, with CMU, and they suggested a phase change material that sort of optimized its melting point, fits right within the, I guess what you'd call the operating range of thermal comfort for the building. So it sort of changes phase and introduces heat and absorbs heat to remove it from the space when we would want it to, based on the sort of occupancy profile of the building. We also have a sort of unique there in the CSL is we have some shade systems, particularly in the atrium, which allow us to sort of, when we don't want to get unnecessary solar gain in that space, we actually have thermal shading systems. They're sort of combined light shade and thermal shade. So they sort of serve two functions depending on what mode we want them to operate in. Ultimately, the other piece, which I think we were highlighted many times by Craig, high envelope insulation values. Pretty much everything we're using on the envelope of the building was sort of at the highest end of what the industry standards were for insulation values on the envelope of the building. Ultimately, we're entirely powered by renewable energy. Combination of geothermal, solar, and wind support all the needs of the building from an energy perspective. We have extensive indoor environmental quality, water and energy submetering and monitoring. So in terms of our long-term performance, we're constantly analyzing the building and tweaking it. So I think that's always a principle that is important to highlight. Is it's not, the work isn't done once construction's completed. We're constantly intervening with this building and looking at ways to improve its performance over time. And then sort of the other piece of that is we're always doing this ongoing post-occupancy evaluation to see how, what could we do and what are the customers and occupants of the building telling us about its performance. And then ultimately situations like this where we're sharing and educating others about what we've installed there and some of the learnings that we've ultimately derived from that over the years since 2012. This just gives you a good idea of what the site overall orientation is on not just the Phipps campus, but ultimately you can see my big blue directional arrow pointing north. So you can see how the footprint of the site is oriented. There's a pretty extensive south facing side of the structure, and the north side, which you see a little bit more shading and plantings on. And then there's a slimmer east-west profile on each side of those. And then in an upcoming slide, you'll see a little bit of how the daylighting in the facades relate to that design. This is our entire offset system of photovoltaic. It's actually, because we used the majority of the rooftop as a green roof, we had to site the PV on rooftops of other parts of the campus, other buildings. So what you see here is our exhibit staging center, some ground mount arrays next to the exhibit staging center, and then our special events hall flat roof all have photovoltaic installed that's supporting and offsetting the use of the power in the CSL. This is the small demonstration wind turbine, actual wind turbine that we installed, which also sort of complements or supports the renewable offset for the CSL building and project. It, I always say with this one, ideally it should be at a higher elevation, but because of restrictions with the city, it is not necessarily at its ideal or maximum elevation to produce the desired or the maximum output. So it does get some interference and windbreak from the structures you'll see behind it, the production greenhouse and some of the adjacent structures. So it does produce, we monitor it, track it, it does produce, but there's certainly the opportunity if it were sited at a higher elevation to have a lot more production associated with it. These are some photos of the geothermal installation for the site. It's a total of 17 wells sited just adjacent to the property, most of which are sort of right on the edge of our parking area for the site. You can see here demonstrated he's setting the supply and return piping in one of those vertical wells. These are just examples of our operable roof vents in the atrium. And on the right-hand side, you'll see some of our, each of the workspaces has upper windows with operable vents that open based on certain outdoor air parameters, that those will open up and allow natural ventilation to occur in the actual occupied spaces as well as in the atrium. This is a view of the nice, really nice picture capturing the green roof and full bloom. So again, you can see that just simply it's sort of an extension of, because that the project is built into the hillside, it almost looks like it's an extension of the existing grade of the upper portion of the campus. You sort of traverse right from the upper campus onto and invited into the CSL's rooftop and the garden space there. This is a shot of this soy-based phase change material. Sort of the unique melting point property of this lends itself to a melting cycle that allows it to, primary benefit of it is during the nighttime, there's actually the phase change of the material actually is adding additional heat to the space, allowing us to maintain over time, overnight, particularly in the winter, it's returning heat that was stored in that sort of latent heat of phase change of the material back to the space. So it's sort of acting as a source and sink when we want it to inside the walls themselves. To do other specific parameters, they're looking for inputs on for the COTE spreadsheet. One is related to lighting power density. We did, fortunately, through the energy modeling, have a target parameter for that. Our installed lighting power density was 0.75 watts per square foot. When you look at the tool itself, that put us at roughly, just below 30% reduction over what the benchmark site for, in this case, it was a office / educational space, was the majority of the footprint of the building. That is the benchmark density for lighting power density that we used for this project. One thing I will note is if you go into the tool, if you go into the current tool that's referenced in the COTE spreadsheet, it's going to the 2021 International Energy Conservation Code, and it's a significant step up because of all this solid state lighting technology. So 0.75 is probably no longer irrelevant. For 2015 targets, yes, we did actually exceed our target parameter and come in below it. But most of the spaces across the board you'll find have significantly reduced watts per square foot in these new International Energy Conservation Code target numbers for the various different spaces. I was a little surprised to see it goes down pretty substantially with all the low wattage from the solid state lighting that's introduced now. Last parameter that they're asking for input on, it was a little challenging to come up with and approximate because I couldn't find it in any of our existing project data, but it was a rough estimate of what the facade's window space was of the sort of envelope of the building. And when you run those numbers, it comes out to a roughly 0.38 window wall ratio number. So good to know that we were in the target range of 30 to 40%. We're sort of towards the higher end of that, but when you see some of these slides, particularly on the south face, we've got a pretty significant footprint of windows. I mean, I think on that face, I was getting close to 50% of the south face is actually covered by window space. Obviously on the north face, slightly less, but still not insignificant in terms of the coverage of windows versus wall. And then a little bit less or more modest on the west and east faces of the building, which are in general the slimmer profiles and the sort of rectangular footprint of the site. I think that covers everything I had for the energy piece.
Next section is on resources. Let me share my screen. Alex Coe is dealing with that one. Alex is a research manager at the Living Building Challenge, Living Building Product Challenge. He studies embodied carbon, material health, environmental impact. He's certainly a materials expert. He has training in chemistry, toxicology, life cycle assessment as he came up in the business doing nonprofit consulting, and really has a heart for environmental justice. He's a living facilities associate, the lead AP, has credentials in G-Pro. He's got a master's degree in environmental management and a BS in chemistry from Yale. He claims he's a proud low-income first-generation college student. So take it away, Alex.
Awesome. Thanks, Fred. Thanks, Brad. So I come to the topic of design for resources from primarily a manufacturer and data piece, and not necessarily from the design perspective, but I think a lot of the topics kind of inform a greater design strategy. And so the prompt from AIA is that good design depends on informed material selection, balancing priorities to achieve durable, safe, and healthy projects with an equitable, sustainable supply chain to minimize possible negative impacts to the planet. And guiding questions that I'll just splash on the screen. I think it's interesting that the AIA's Architecture and Design Materials Pledge really reflects a lot of these prompts and guiding questions when considering, evaluating the products and finishes that are specified on a daily basis, as the quote says. And it's a voluntary commitment that individual firms can sign on to and commit to implementing these 5 guiding principles and to the extent that they can in their firms. And so I just thought it was cool to tie that connection to something that the broader AIA has supported. Because we're talking about FIPS, CSL more closely, I just wanted to share a couple recently certified projects by ILFI that I think had some really cool materials achievements. And for me, the design for resources explores this tension between what's tangible and what's hidden or embodied with respect to emissions, impacts, and supply chain. And with the Candida building in Atlanta, that team, one interesting approach they took was creating a materials committee comprising sustainability experts from their contractor and the architect to collectively find materials suited to the project requirements. And I think what's interesting about it is that it's in a humid southeastern US climate. So there needed to be insulation as well as making sure that energy consumption would be reduced while operating in that climate. With the Harvard Science and Engineering Complex, one story that came out of that project is the team investigated over 6,000 materials options in the construction process. And some things that are in that type of projects, like lab equipment, aren't necessarily always common and asked for the materials questions of substances, embodied carbon, and all these things. So just two projects that we were able to support through certification pretty recently that I think had some great stories. Looking at the scorecard, there are 5 individual sections, and one set of the prompts speaks to materials selection and factors at that individual material level. And the first are environmental product declarations, or EPDs, the use of reused, recycled, regional materials, third-party certified materials, FSC woods, and then the act of considering waste diversion during the construction process. So I think what much of this gets at is the hidden and embodied emissions incurred by actually creating and manufacturing materials. So we can think of operational energy that shows up elsewhere after occupancy, but there's a whole set of impacts that are associated with the greenhouse gas emissions arising from manufacturing, installation, maintenance, disposal of building materials and packaging and associated pieces during the construction of buildings and infrastructure. And I think in the sort of general discussion, we see steel and cement with a lot of focus because of their energy intensive processes to make those raw materials and to extract the raw materials that go into them. Within the practice of life cycle assessment at the building scale, there's the tool called the EPD, or Environmental Product Declaration, and that's there's a whole vernacular around what scope and what letters and numbers refer to in that sort of type of disclosure, but usually the focus and the discussion is around A1 to A3, which you might also be familiar with as cradle to gate scope. And for the individual product level, that's sort of the concept of focus, because that is what is pretty standardized for manufacturers that they can directly control. So anything past the gate, or the sending from the final assembly facility to the project site, those are highly variable and usually are pretty project specific. So raw material extraction and transportation to the manufacturing site and the actual manufacturing process are pretty much what the manufacturer has the most control over, and that's sort of the most secure data piece of it. And to kind of explain that acronym a little bit more, if you're not familiar, EPDs are life cycle assessments of products that simply are designed and meet additional sector specific requirements called product category rules that guide data quality assumptions and comparability of results within a product type. And that snapshot in the lower right corner is taken from the EC3 tool. It's a whole building LCA modeling tool, as well as a database for EPDs of products. And at the moment, a lot of what we see is structural and envelope type materials and interior finishes. And I think that there's a heavy sort of focus at the moment on concrete and getting discrete data pieces for that material. The section on reused, recycled, regional, I think kind of speaks to mitigating emissions associated with manufacturing, because there are 3 different approaches that reduce that impact of a globally sourced product in different ways. And so, I think there's the idea of always considering materials reuse first, because that completely eclipses and avoids a lot of the emissions associated with manufacturing something, especially if it's in situ and you can just build around it if it's a reuse project or adaptive reuse. Recycled materials can mitigate or eliminate some of the impacts associated with raw material extraction and processing. Regional materials mitigate emissions associated with transportation to the project site. That in some ways can be counteracted by the fact that a lot of building products have global supply chains that may get some parts from the US, but may get some parts from Asia. Construction waste diversion mitigates impacts, I think, with hauling and landfilling and other end-of-life scenarios. And just something that is in the spreadsheet as one line, but doesn't feel the most connected to the rest of that section is FSC wood. But there's just a general sort of understanding, and there's one study that shows that wood sequesters significantly more carbon than wood from traditionally managed forests. So there's an argument there to include it in this sort of greater idea of reducing process emissions and construction emissions. The other part of that section talks about third-party certifications, and it's also really also thought of sometimes as a logo soup or an alphabet soup. But the goal of them is to aggregate and rate multiple dimensions of sustainable performance, and I think reduce the amount of work to find products that meet performance and project requirements. Part of why they've proliferated so much is a lack of federal regulation or a lower floor of performance in terms of what products need to meet. But some are federally sponsored as well. I think that there are several sort of spectrums in this world, which include being single attribute, maybe focusing on health or water efficiency, versus multi-attributes, focusing on different dimensions and product impacts. There are those that are broad and represent consumer products generally, building products generally. There are some that are more exactly focused to one product sector, such as flooring or office furniture. And there's a proliferation of them, but there's also, I think, a wealth of existing resources to provide designers with at least a basic and essential understanding of what they're intended to communicate and what they would mean toward meeting project requirements. At the same time, that proliferation and noise has led to emerging approaches to analyze and assess materials from a holistic approach. So one example that I've seen recently is this Brightside tool from Brightworks Sustainability, and it looks at different tertiary and secondary factors that it rolls up into these 6 main categories seen here. And then the output is a calculated single numerical score on a scale of 0 to 100. So that can help either expedite materials specification or give those that are in that position at least a quick indicator of, should I look further into this material or should I discount it, if you're subscribing to this holistic evaluation. If we kind of zoom out to the larger level at the project, the other 2 sections prompt the user to think about embodied energy and carbon, and kind of doing a life cycle assessment and quantifying impacts across the whole life cycle of a building. I think that there's a few compounding forces that amplify this importance and are kind of leading this area. And there's consumer preference. Occupants and consumers are ready for businesses and firms to demonstrate action on climate. There are investor kind of pressures to demonstrate transparent and science-based reporting and impacts, and showing that you are considering and developing the capacity to make these analyses, and challenges in the entitlement process of developing and securing a building. So I think that there's an economic rationale that kind of underscores what we kind of see as the data piece, and I think also this moral and justice imperative of materials, because there's the impacts and the numbers, and then there's the health concerns of VOCs and things that that are factors of material selection, but I think are covered a little bit more in the design for well-being part of the framework. This is a very in progress, incomplete comparative matrix between some of the major LCA tools that and plugins that we've seen. This is compiled by some colleagues at ILFI. So I'm sure that there are some that are missing and some that maybe have some outdated information, but I think it also kind of goes to show that there's been an increase in a maturity of the tools and plugins available to meet the demand of the types of analyses that designers might want to be doing these days. And the scorecard actually, the super spreadsheet actually links to a carbon estimator tool that I clicked on, and it looks like it dates back to 2007. And it's kind of rudimentary in how it operates. And there are a lot of assumptions that we have a lot more data for now that these powerful tools can really process and give a more specific evaluation to a project. And then there's even more on this page as well. So I think that kind of marrying those two ideas together, you can improve how specific an analysis is at the project level by finding more discrete data points of EPDs. I think identifying software packages that integrate most seamlessly with existing tools and practices is a good way to on-ramp into doing more of these analyses. And something I've heard from colleagues at ILFI is to emphasize exploring these options early in the design process, and maybe just doing additional baselines and doing additional modeling early on, in charrettes early on in design. So you present the data and kind of can make the case to an owner or a stakeholder earlier on that there's a design potential in the design case to integrate some of these lower impact options, and thinking about materials that early on. Just quickly, something that the Carbon Leadership Forum, a group advocating for reducing embodied carbon of the built environment, kind of thinks about is that there's the way to optimize reduction strategies at the project level, there's the system level, and then there's procurement practices, and there are tools to support each of these strategies. And then there are policy levers that are longer term in scope, but will contribute to supporting these systems in the medium and long term. I just wanted to highlight that the AIA resources date back for 5 years at this point in terms of discussing materials and some of the risks and opportunities associated with it. And this is just something I started attending earlier this week, but there's a healthy materials series put on by different COTE, CLF, and USGBC chapters in Bureau Happold over in the West Coast, and they're actually doing a really good intersection and review of healthy materials from the health perspective as well as the embodied carbon perspective. So if you just search CLF SF Bay Area, it's a lot of letters, you'll probably find it, but happy to send the link out to anyone if they're interested. So with that, I'll just pass it back to Brad.
Thank you, Alex. Not seeing. Hold on a second, I'm not seeing it.
Brad, do you want to wrap up that one after we go through Patty's? Cover them both together at the end.
Hold on, say it's not showing in the. It's not showing in my options to share the screen. Oh, here it is. It might have closed in the background. Here we go. So design for resources, I guess with respect to, I know we're sort of running behind on time. I'll try to go through this one pretty quick. The inputs on this section that were pretty straightforward. First one being the embodied energy, or sort of a calculation in the tool of the embodied energy. It makes reference to a web-based portal called Build Carbon Neutral. The nice thing about this one is it's very streamlined. The inputs you see here is just a screenshot of the summary of what I had to input to actually come up with the estimate through the tool. So it was maybe a handful, 5 or 6 different entry points that were needed. Obviously, as Alex referred to before, there's a lot of more complex and involved models for embodied energy. I believe the one we used was from the Rocky Mountain Institute called Green Footstep. But for the purposes of the tool and I guess consistency in comparing projects, everybody would be using this same calculator. And experience with it was very, very simple, minimal number of inputs. So certainly most projects will have those parameters you need to input readily available. Sort of the conclusion of the output was our embodied energy benchmark from the benchmark was actually representing fairly well, which was certainly good news for us to hear. That is that we're at about 42% of what the benchmark would be for embodied energy based on largely the materials of construction and footprint of the site, as well as some of the usage of the site and sort of native plantings and how the site was restored. Second was a simple question of whether a life cycle analysis was completed. In this case, yes, one was sort of unique in the sense that it was done. We didn't, as an organization, have a lot of experience with life cycle analysis. So Phipps had partnered with some of the staff at the University of Pittsburgh. Faculty and students were involved in sort of this collaboration. So there was sort of shared learnings there for both parties, and we were able to leverage some of the expertise from the university staff. I couldn't pinpoint what the specific name of the software was, so I unfortunately couldn't tell you what the specific model was that they used. The major structural system is sort of generally speaking, it's steel from all the major structural elements of CSL. There is a decent amount of concrete, so but I sort of chose steel just because that probably is the majority of it. And when you look at the material inventory, it is the larger proportion of the structural elements. And there is some concrete largely associated with the atrium structure itself. Some of our major strategies for ultimately reducing embodied carbon, the primary one was our selection of materials of construction. And like anything else, it's a trade-off. Concrete, steel, wood. Wood has some embodied carbon benefits, but getting FSC certified materials in our geography is challenging for a large-scale project. Probably gotten a little bit easier now, but back in 2011, it was a pretty significant challenge for us. So that was factoring into it. Plus, we are the steel city, so it made sense. We had a lot of regional source material, and it also reduced the other elements of the embodied carbon footprint by sourcing most of that steel from someplace within 20 to 30 miles of the project site. And that sort of goes to this other, what was another major strategy for reducing embodied carbon. And our response in that was a lot of, and you'll see in the specific numbers we cite in the upcoming slide, a significant portion of the spend for materials came from locally sourced suppliers of those materials. Some of that's a benefit of the proximity of Pittsburgh and the manufacturing base. Others were sort of a concerted effort to identify suppliers that were within a certain geography. The third input for this section on resources in the COTE spreadsheet, and I'll be transparent about this one, is number of materials specified with EPDs. And I think what highlights this more than anything for me was what Alex shared with, there's a entire slide full of different EPD entities and organizations that could be referenced here. Back in 2011, there were a lot fewer of them. They've sort of proliferated over the last 10 years. So there's certainly a lot more of that accessible to you in specifying materials for a project today than there were back then. So I pulled specifically 4 examples of ones that we know we highlighted and that were readily accessible. But in all likelihood, if we went back and did a exhaustive review of all the specs and material data for the project, I would suspect we're probably in the 20 to 30 range of different materials that were incorporated into the project, of the hundreds of materials that did have some form of EPD. So just for transparency, these are 4 examples we pulled, which we knew were readily available based on the material specifications. One was our carpet tile. The second was EcoBat insulation, some of our insulating material within the project. PPG's glass, obviously another local supplier. The insulated glass was Cradle to Cradle certified silver, and some of our DuPont Corian countertops were SES certified. Construction waste diverted. This one actually was something that was a learning experience for me as well, going back through some of the project record on this. We achieved a unusually high percent of construction waste diverted from landfill. So the first input to this, it's a fairly straightforward question. You're typically going back to, in this case, we had it through both our LEED and LBC certification documentation. So we actually have a tracking and measurement spreadsheet for construction waste, which sort of tallies everything and measures it. So it was a fairly simple exercise for us to pull this out for the CSL project. The metric was already calculated from that at 97%. So there's not a whole lot more there for us to sort of scrape from the bottom to ultimately divert from landfill at that point. The method determined was ultimately measured. There's quite a bit of data input and analysis. A lot of this in the case of the construction waste is weigh tickets from different haulers and recycling and recovery facilities that have to be tracked and then tallied all together. So I guess the other inputs that they're asking for is sort of the unique identifiers for this project. There's a number of cases where they give you in the tool the opportunity to highlight things that would be considered unique about this project. So that's sort of a theme I've been trying to highlight, is as we've been going through this tool, like pick things that are unique about this project that make it stand out from the others, since this is associated with an award submission and recognition process. So one notable strategy here was that our prime contractor on this, Turner Construction, had developed a pretty elaborate construction waste management plan. And I think that when you look at the details of it and the history, was a large part of why it was so successful in achieving a 97% rate of recovery. What they did within that was they hired and assigned responsibility for this, specifically contractually, amongst a couple of different parties. One was a company called Allied Waste Service, and the other was a company called Noralco Corporation. And specified within that construction waste management plan are a lot of details about exactly who, what, and where this material is going to go. So it was actually mapped out in advance of the actual construction. We weren't scrambling to find out, well, who will take, this type of ferrous metal, or who will take soil of this type. It was all spelled out and pre-approved, knowing what we were going to likely run into in terms of construction waste. Another key thing that I found was interesting, and I know being on a lot of construction sites, we struggle with, is wrangling all the different contractors. So in this case, one thing they did with Allied Waste was they had open containers where they were collecting the material, and they took it to their own facility and sorted it off site. So they took a huge component of policing out of the project by simply assuming that they were never going to be able to get all these contractors to, fill 12 different containers with different types of materials. It was all going in a single container at the site during the construction and excavation phases of the project. And then they took that container off site, and people with the knowledge to be doing this were sorting and segregating it so that it wasn't basically being contaminated and winding up in landfills. The other thing I just wanted to highlight here was LBC has a pretty rigorous expectation with certain materials in terms of construction waste management, either 100 to in excess of 90, and in some cases 95%. We certainly met all of those, and in this case, individually soil and biomass, we were able to achieve 100% and overall 97%. We sort of well exceeded the lead criteria, and then ultimately the project was certified to sites as well, and similarly there were some shared targets for that certification system that we also achieved, and then theirs were a little bit more modest in terms of the overall materials diversion rate percentages they needed us to achieve. And this was really just for more than anything reference point for those folks who are in the industry and looking for, because I know sometimes this can be the biggest challenge, identifying facilities that we successfully use for construction waste diversion and reuse and recycle. So I just, from the waste management plan, embedded them in the presentation in case anybody wanted to reference any of those providers. Number 5, and I believe this is the last input on the resources section of the COTE super spreadsheet, sort of by spend evaluation of recycled regional materials. So it asks for total materials cost out of the overall project cost. It self-populates from an earlier field, the total construction cost. So this actually was another thing that I was a little concerned with being able to identify. But fortunately, through the LEED framework and LBC frameworks, we already had all these materials tracking sheets, which had them by spend. So we were able to, I was able to pull that information from a summary spreadsheet. So it turned out to be around just under $3 million of total materials cost on the project. Within that, the total cost of recycled materials was roughly 28%. Total cost of regional materials, sort of the loose definition of what would be within a certain radius of sourcing from the site, was rather impressive. And I think that largely speaks to what I was referring to before, which is Pittsburgh has a lot of industry associated with construction materials in the region. So we were able to source a lot of the bulk materials from somebody within our region locally. So that total was around $2.25 million of that overall spend, and percentage wise, getting close to 80% of it was sourced regionally. There's not an enormous amount of wood incorporated into the project, but all of it that was FSC certified and is documented in those material tracking spreadsheets. In terms of notable sort of distinguishing our project specifically to highlight one of the things we felt was a success, sort of unique, not necessarily in the terms of the volume of material, but certainly from the aesthetics of it. The majority of the exterior siding is produced from a salvaged barn wood from various different farms within Pennsylvania. So when they demoed these barns across most of rural Pennsylvania, they were able to plane and resurface that wood and convert it to siding, which you'll see covering most of the exterior. And it's very aesthetically pleasing and actually gives sort of a warm aesthetic to the site as well. So not only are we avoiding raw materials, we're actually producing a pretty pleasing aesthetic decorum for the outside of the building. One thing that did jump out when you go through the sort of exhaustive spreadsheet of purchased materials, steel and metals. I don't know that this was so much our strategy as it was, but virtually every material that it has a metallic component or source material that's steel or other form of metal has some post, if not a enormous post-consumer recycled content. It has at least some portion of it. And unfortunately, when you go to a lot of the other materials, including even plastics, there's a significant drought in the number of available materials, or certainly ones that we used in the project that had any, if that, of a post-consumer recycled content to them, which was sort of enlightening to me. Is hopefully we've progressed from that since 2011 and see a little bit more of that in terms of post-consumer recycled content in these plastic products. One that we did that is a plastic product that we incorporated into our rainwater harvesting system was this Atlantis D rain tank product. It's essentially looks like a big milk crate that's buried in the ground and can be configured in enormous rectangular or square shapes for storage volume of rainwater. That is actually entirely 100% post-consumer recycled content plastic. So that was one that definitely stuck out when I was going through all these plastic components, that this particular material was the only, or if one of the only plastic components in the materials spreadsheet that was 100% post-consumer recycled content. The other two notable regional materials that we wanted to highlight, and this is sort of specific to our renewable energy element of the project. It's not easy. Anybody who's done renewables knows that a lot of the manufacturing occurs overseas. You know, you gotta do some work to pinpoint availability and supply of panels and associated inverters and electronic equipment with renewable systems being sourced not only from North America or the US, but certainly local to Pittsburgh. It's even challenging as well. We were able to, at that time, bring at least a US manufactured photovoltaic panel in. I know since 2011, there's actually a few manufacturers that there might even be a few in Ohio that you can leverage. But at the time, it was very limited. And one of those was actually from the West Coast. So those panels were sourced from Solar World, whose manufacturing is in Hillsboro, Oregon. So certainly wasn't from overseas, but was from the West Coast, which is not a short distance from the Pittsburgh region. And the inverters themselves were also manufactured and sourced within the US, but a significant distance, probably one of the longest distances of source materials we had, the panels and the inverters coming from Denver, Colorado. And the other one that we were going to highlight was, although we had those challenges with those components of the renewable system, the steel and aluminum racking was something, because of all that's available in terms of the supply chain in Pittsburgh, was from like literally 20 miles away in Ambridge, Pennsylvania. So there's always a trade-off with any of these things, is if you look at it and make a concerted effort to try to reduce those footprints, it can be done. But in some cases, your options, you know, you're picking the best that you can find that's available in order to meet the end goal of the project. And this is just a snapshot of what the recycled barnwood looks like. We actually have a small demonstration of that with one of the walls, cross-section of the walls of the CSL building in our atrium for guests to sort of learn a little bit about the building. You can see how sort of nice a form it is, nice wood plank siding.
Okay, we're going to move quickly to Patricia Kelly. She's an architect who's associate principal at Boland Swinski Jackson. Her approach to architecture centers on the balance between thoughtful, community-driven design and environmental consciousness. She's a highly collaborative architect committed to inclusivity. She's a graduate of Carnegie Mellon University and a leader for sustainability within BCJ's practice. She's a LEED accredited and WELL building standard accredited. She has a wide knowledge of sustainable design strategies that are exemplified in her work. She was the leader of the recently completed Frick Environmental Center here in Pittsburgh, which was the world's first free and public living building challenge targeted project. She's committed to advancing design excellence through knowledge sharing by regularly speaking on design sustainability, biophilic design, and equity. She's an AIA member, COTE committee, lead AP, and WELL AP. So, Patty, have at it.
Great, thanks, Fred. I'm going to share my screen here. Great, thanks. So we'll go quickly through these. These are the guiding questions that I will address in the case study that I'm going to share. So designing with ecosystems, even though this section of the AI framework, it's certainly not as intensive and technical as the water and energy and materials portions. It's still a very important element of the framework. And so we'll chat a little bit about what it actually means. Designing for ecosystems is very much about connecting with the natural world, specifically focusing on each project's local environment and local flora and fauna. When a project's situated in a natural setting,
designing for ecosystems still should be a very intentional effort, although that design effort may be more simple to implement. So here, this photo is of the Frick Environmental Center, which is the project that Fred had mentioned. This is a living building challenge facility similar to the CSL, and it's located here in Pittsburgh. But you could see in the photo, in the front of the photo, are the constructed wetlands, which use native vegetation, and they really do become a sanctuary for birds and pollinators. However, when a project's situated within an urban context, designing for ecosystems can be a little bit more challenging. So we'll talk a little bit about what that looks like. So basically knowing that Brad's going to be talking again about ecosystems with respect to the Center for Sustainable Landscapes, which is obviously in a very natural setting, I wanted to share a different kind of scenario, which is a project situated within an urban context and actually pretty close to the CSL. So this project here is Ansys Hall at Carnegie Mellon University, and it's designed for their College of Engineering. It was recently completed in 2020, and it's a 4-story makerspace facility with also supporting office and lab space, and also houses the Dean's Suite for the College of Engineering. So we'll zoom out a little bit and look at where this project is situated. So here's a larger campus site plan, and the dashed line indicates the original Hornbostel Mall. So Hornbostel was the designer of the original portion of the Amuse campus over 100 years ago. And the Ansys Hall building is located at the far corner, which is located in red. And it very much is the culmination of a really strong axis of buildings, the Baker Porter wing along the south edge of the Hornbostel Mall. And the building is really tucked in almost where a building shouldn't be. It's sort of tucked in between a variety of buildings, and it sits at an elevation that's lower than the mall. So you'll see what that actually does to the building itself. So zooming in here now, this is a view of the building site plan, and the site was originally a parking lot. Honestly, it was just completely hardscape, and it was a mix of asphalt paving and concrete sidewalks, so really no vegetation at all. And the new building was conceived to nestle between all of these existing buildings while maintaining a pedestrian pathway that cut across the site. It was a public pedestrian pathway. So it technically abuts 4 existing buildings at 7 unique levels, just because of the way that the existing buildings and their sort of elevation change within the buildings. So it really is tucked into this corner of campus. The program requirements for this building were very ambitious, and so they pretty much wanted to use as much of the site as possible for the building and as much of the exterior portion of the site for the programming element. So actually extending outdoor learning, that was a really important factor. So it's a very, the amount of building to site is very high in this particular context. Again, wanting to share sort of an urban example. So how does this building support regional habitat restoration is one of the questions, one of the guiding questions that we want to talk about. So because of the high program requirements, our landscape strategy was to really incorporate focused areas of vegetation within the site. And although those areas in and of themselves are rather small, they were large enough certainly to support, birds and pollinators, which is a large improvement from the pre-construction conditions of being a surface parking lot. The vegetation that we included in these focus areas, of course, is native landscaping. And the design strategies we used included, again, for this particular urban context, rain gardens and green roofs. So this is sort of diagrams of what generally rain gardens and green roofs looks like. So how can the design support the ecological health of the place over time? Well, this actually ties, because our design for ecology also intersects with our strategies for water. So those two elements sort of tied together, but because we focused on these particular elements such as green roofs and rain gardens, the emphasis on the stormwater management strategies really does improve like the regional ecological health in several ways. And Brad mentioned this when he was talking about the water strategy. So basically these green infrastructure design strategies minimize stormwater runoff, which in turn decreases storm sewer overflow, which is a particular problem in the city of Pittsburgh, because that storm sewer overflow goes into our waterways and it really decreases the overall health of our rivers. So by using green infrastructure strategies and mitigating, having our stormwater go into the combined sewers, it really does help to improve the local waterways, our rivers, and sort of the regional ecology of our area. So looking back to the site plan again, the green roof is located sort of at the upper level above what is the makerspace portion of the program. And it's at the same elevation of the historic mall. And we'll take a look at a picture of what that actually does and providing connections to adjacent spaces for this building. The rain gardens are located within the outdoor paved area, which is what we call the maker court. And they actually, again, because they're green infrastructure strategies, the stormwater that gets sent within the rain gardens actually has a support system, which they overflow into an underground detention basin. And that is effectively a capture and a slow release system so that instead of feeding directly into the storm system when we have a large rain event, it contains the water in such a way that after the rain event passes, it will slowly release out into the storm system, the water that hadn't infiltrated. So this overall system really does, again, help to improve the regional ecology of our area. So here's a view of that maker court, and this was taken before the vegetation really started to take off. But you could see the rain gardens in the foreground. Again, one of the reasons why this paved area is so large is because they want, from a program standpoint, they do want to bring the program outdoors. This is considered sort of an extension of the program space, and they want to be able to build and work on their experiments and test their cars and whatever else they're building within the high bay of this makerspace facility. So we did need to have this sort of large paved area, but we did try to incorporate these green infrastructure, stormwater management, and ecology design elements, including these rain gardens here, and then up above where the railing is up here, that's where the green roof is located. So how can the design build resilience while reducing maintenance? So by using native vegetation within the rain garden and the green roof strategies, the vegetation, not only does it survive, it really does thrive without very much effort. So irrigation is not needed at all. And the ongoing maintenance, like what you have to deal with formal landscaping, is really not needed within this scenario. Sorry about that. Unmuting. 1 second. Back. This is the Ansys Hall building here on the right-hand side, and the green roof still to be grown in, but will effectively replicate an adjacent green roof, which is something that you see in the foreground here. it really does we're using natural vegetation again to minimize the need for irrigation. So one of the final questions within the design guidelines were, how can the design help users become more aware and connected with the project's place and regional ecosystem? So as the AIA sort of put it, good design mutually benefits human and non-human inhabitants, and of course, our overall planet. So anecdotally, we know that connection with nature can really have a positive impact on people, particularly within a learning environment like at CMU, where the drive for high standards of excellence is really very strong. So connection with nature can absolutely, decrease stress, increase creativity and cognitive function. And by reducing something like as simple as reducing the need for formal landscaping and actually designing these native and wild landscapes, even if they're small, even in a very urban context, you can absolutely heighten user awareness of the relationship between the built and the natural environments and instill a sense of wonder about the world around you. Thank you. So Brad, I'll pass it off to you.
Thanks, Patty. Design for ecosystems. There's a short section in terms of its COTE spreadsheet inputs. It's largely asking for various different footprint parameters of the project site. For us, most of these were available for the CSL's project because they're already incorporated into either a lead materials and component of the submission or a living building challenge component submission of the various different footprints of the site and sectioning of the site. For us, there were the three or the four components that we're incorporating in. First was green roof area on the third floor or the third story of the CSL, which is just under 4,000 square feet. Overall total building footprint area, which was just under 11,000 square feet. Surface parking area, just under 40,000 square feet for the project site. And then ultimately the remaining space, the area of additional on-site hardscapes, various different walkways, hardscapes that are, related to the landscaping features themselves, was about 16,000 square feet in total. Then it ultimately calculates for you what would be the area of the total site that is vegetated post-development as it relates to the overall site area. And then it calculates a % vegetated post-development. For this particular project, we were just above 50% was still vegetated post-development. Area of the total site that's vegetated pre-development. And I think you'll see in some of my upcoming slides the dramatic shift from pre-development to post-development with respect to not only the quality of the site in terms of its ecology, but just the sheer extent of it. It's pretty dramatic. So the pre-development estimate of the vegetation on the site was roughly 25,000 square feet. So sort of calculated metric for vegetated area increase in terms of what was done to promote the increase in vegetated area. We were at roughly 40% for the CSL's project. And then the second input for this section of the spreadsheet on ecosystems, it's another site parameter where they're asking for the total site covered by native plants post-development, which for our project was pretty simple because the entire planting plan for the CSL's undeveloped portions of the site were for native plantings. There was a specific concerted effort made through the planting plan, which you'll see in some of the upcoming slides, to basically take advantage of high value native eco region plant communities. And there's reasons why, and I'll get into a little bit more details of why that sort of was in the wheelhouse of Phipps Conservatory to sort of endeavor into that for the CSL project. Area of total site covered by turf grass post-development, also very easy for us in this case, 0. So the input was, there is no turf grass post-development. And it again sort of reflected the parameter outputs pretty well. As native plant, we're at 100%. We maximized what is the sort of indicator parameter here in terms of amount of vegetated area, and with native plantings was at maximized at 100%, 0% turf grass, and the percent of the overall site was roughly half the site is encompassed by native plantings. This is actually extracted from one of the lead submissions, sort of overall site plan for the project boundaries. So you see the perimeter of the site that was evaluated under sort of the lead certification process, as well as same footprint for LBC. It depicts the building footprint, the hardscapes, both the paved parking areas, as well as the hardscapes for landscaping, mostly just access pathways to and from the CSL and the adjacent buildings in the upper campus, and the lagoon footprint, which is water surface, which is incorporated ultimately into the what they'll qualify as the vegetated site. And you'll see in the upcoming slide how that's characterized in terms of the overall eco-region strategy in the planting plan. This is just what I incorporate in here is a real nice rendering. So it gives you an idea of what the architect's vision was for the CSL site. And you'll see again it's definitely a vision that was created in their minds, because when you see what the post-development conditions look like, it looked nothing like this. It's a dramatic shift in the landscape. And there's a number of reasons why that was the case from the use of the site post-development. Or pre-development, I'm sorry. So this is actually a planting narrative that was encompassed into the LBC certification submission package. And it was really what I found to be a really nice way to highlight what the overall sort of layout or footprint of the planting plan was looking to accomplish. And then what was really nice is they incorporated in these photographs to give people an idea of what type of planting scenario they're looking to incorporate into these various different parts of the site itself, as far as the restoration plan. And you'll see it's a very concerted effort that was done on the part of the planting narrative and planting plan for the site. What they did was they went back and evaluated sort of these exceptional reference plant communities that were native to ecoregion, Pittsburgh's ecoregion, which I referred to as EPA level 3 in their sort of analysis of ecoregions. And based on that sort of research, they came up with a planting plan for each of these individual categories. I think there's a total of like 8 or 9 of them, which would maximize the ecosystem value of the planting plan. And it was designed to the topography of the site, contour, so it's sort of like built into a hillside. So a lot of the thought process around what was sited where had to do with the drainage of the site. So you'll see where there's the sort of rain gardens for the drainage system, and then the water's edge, as well as the constructed wetlands. All these things were related to the overall drainage pattern and the water systems layout of the site as well. So they all integrate together into what's suitable for all these different portions of the site. So again, highly researched, highly specified in terms of the plantings that we were putting in each of these areas. Not surprising that we have FIPS offers a pretty extensive programming in sustainable landscaping courses. So we had a lot of resources we were able to leverage for this particular project that I don't think everyone else would necessarily have. So I always like to mention that this was something that was sort of aligned very well with FIP's overall mission and sort of the horticultural science programs we have, which allowed us to sort of take full advantage of identifying what would be the maximum ecosystem restoration elements for the site and native to this portion of the Pittsburgh region. This is what I was referring to before, is when I flipped from pre-development to post-development, you can see the site was a sort of combination of rarely used existing city DPW facilities and infrastructure. It was an old DPW garage and maintenance facility. which had sort of fallen out of repair over the years. A lot of various different layers of hardscape surfaces, virtually no plant life on most of that at all. And where there was sort of open surface or soil, it was either highly eroded, which you can see just on that hillside, that you can almost pinpoint the erosion from the aerial photo. And where there were trees in place, they were few and far between, where the hillside did have any remaining vegetation. And where the soils existed, they were either stripped away from erosion, or they were so compacted and silty that they were barely able to sort of support any plant life whatsoever. And here's sort of the revelation is, this is the transformation of the site in terms of what it looks like today. You can see not only is in terms of the built structures and the construction of the hardscapes that have all been improved, all the natural landscaping, it now looks healthy, green. You can, even when this one is obviously from the summer, but when you go through the fall transition, you can see the sort of unique nature of each of those sort of eco regions as the fall colors begin to blossom in each area. So certainly a dramatic shift, and I think nothing speaks more to what we were trying to accomplish about the project and this component of it in terms of restoring the ecosystem of what was essentially a barren portion on the fringe of Shenley Park. So even as Patty referenced before, the fact that we're in what would traditionally be thought of as a natural setting, being on the edge of Shenley Park, that portion of our site was literally providing zero ecological value at the time of the pre-development stage. And that wraps it up for everything I had on ecosystems.
Thanks, Brad. Well, we've covered a lot here, and took a little bit longer than we wanted to, but I think it's all been very well worthwhile. You might wonder, we didn't get a chance to talk much about Brad's background, but he's a senior facility project manager at Phipps after a long career with Johnson & Johnson, working in North and South America as a facility manager. So we respect his great knowledge of that facility at Phipps. So we're going to do deal with some of the questions here. We had a question for Brad initially about the FDE tool. Does it privilege mechanical over vegetative water treatment? If so, how would you change the tool to privilege natural systems?
Yeah, I saw that. The only thing I would say on that was the final question. I think it was the fifth question, the last question in the tool. It seems to score, at least the way I interpreted it, if you are mechanically treating stormwater the highest, which maybe that needs to be reconsidered in terms of how they're scoring that because it said I think it said 1 to 5, lowest to highest, and I think the highest was what they were asking for was some sort of mechanical treatment or actual, active treatment as opposed to natural or passive.
Thank you. Ian, that question was also directed to you.
Yeah. So I haven't gone through the spreadsheet in terms of actually completing for a project itself, so not quite as familiar with each of the entries there. But looking at the water tab, there is the step to the irrigation use. There's a plant quality factor, summer evapotranspiration, the plant quality factor based on you can choose different types of plantings, orchard, perennial flower, ground cover trees, shrubs, native plants, irrigation efficiency. It does look like they're taking into some account all of those things, but in terms of how it compares to mechanical, I think like Brad said, the more natural processes should probably could be adjusted a little bit to encourage or benefit on those a little bit more so.
Thank you. There was a question for Craig. Do you see that one, Craig? Asking about passive house strategies making sense in every region equally.
Yep. I see it. I could take it. So basically the question is, can envelope first strategies work in all climate zones? And the answer to the question is absolutely they can, and they do. So if you're asking about specifically Passive House as a standard, I can tell you that PHI and FIAS both have climate specific standards. So they've tuned the building science to meet the climate zone needs from everything from Alaska to a very hot and humid climate or hot and dry climate. So yeah, it does. But more importantly, efficiency is free, basically, we argue. If the building's big enough, why not do it? Because it shouldn't be a premium in cost. We see that demonstrated time and time again. Brussels is codified Passive House, and their costs right now are back to par. Pennsylvania Housing Finance Agency has 3 years of data on Passive House projects, and they show that once the team gets experienced and they get some knowledge on how to do it, it goes back to par in terms of cost of construction. We've seen it firsthand on our projects. So we look at it as a bit efficiency is free. Once you see a Passive House detail, why would you go back and detail it, with the thermal bridge? You might as well eliminate the thermal bridge because we now know how to do that. So, once you start detailing for that, that becomes your new master details, and that persists in everything you do. Beyond energy, designing for Passive House or an envelope first strategy, like I said, is foundationally, it gets at building performance. So you're going to get at resiliency and wall durability, and you're going to ensure that the wall does not have moisture in it and it's not going to fail eventually. It gets at thermal comfort. So you're getting at indoor air and indoor environmental conditions when you have an envelope first strategy. So even when you're in some of those climate zones that you may think that isn't as conducive, it really is, both from an energy and a wall durability and thermal comfort perspective.
Thank you. Alec, you got a couple of questions there. Do we think any of the of those evaluation people are biased by who funds them?
Probably.
Maybe that's an imponderable. We just have to take each one on the basis of who paid for it. Huh?
Yeah, I think we could look very closely at where the data is coming from, what data is overly represented in any calculation, and what biases are included in there. But I haven't really given thought to each one and how they might be influenced in particular. And then to Joshua's question, I don't know if the FDE spreadsheet really has a place to where deconstruction, either calculations or the resources have a place that belong in the spreadsheet. You might have more options to note some reused materials, and I think it could affect your calculations in construction waste aversion if you're having, you don't need to account for some of the mass that needs to be, or associated mass needs to be diverted. So it could affect and improve your proportional calculations. But I'm supportive of deconstruction. We just have to get the infrastructure around it to appear.
Okay, Patricia, you've got a question there.
Yeah, I think every owner would love to be able to mitigate rodents coming into their space and really get the brightest and prettiest pollinators and non-human inhabitants. But to answer the question in some way, certainly our intent for the green infrastructure and just having any sort of natural ecology within that what was a very hardscape site was just to provide really push the owner and say we need to get something in here, and if we're going to have any greenery at all, let's make sure that the plantings are native. We certainly don't want to have standing water, which would mitigate at least the mosquito problem related to the question. So both the green roof and the rain garden don't allow for standing water. But really, any project would benefit, particularly in an urban setting, any project would benefit from having additional native vegetation.
Okay, gang, let's wrap it up. I don't know if Kira is still on here to do any housekeeping. Okay.
Yep. No, I've got everyone's names. Thank you, everyone, for joining us. Have a great evening.
And you're going to publish the access for the recording for others?
We will. It will be in columns tomorrow, a link to it.
Okay. Thank you all. Thank you for those who persisted and stayed to the bitter end. We appreciate it. Thanks a lot.
Thanks, Fred.
See ya.
Thank you, everyone.
Thank you.
Bye.
Thank you, everybody.